Hello, so today we're going to try this fun maths problem, which is to find a matrix M to reflect the vector V in the form xy in the line y equals mx. Now there's two things that we need to note first of all. Firstly, if we have a graph with let's draw a random line like this is y equals mx, there's a few ways of writing this. Now of course we have the classic y equals m times x, where the m is the gradient. But if we think what really is a gradient, well, it's the rise over run, i.e. how much we go up for every unit we go along. Now we can say, let's let this angle here be theta, in which case if we have one unit of the graph, let's say this is a length 1, then this is going to be the sine of theta, and this is going to be the cosine of theta. And if you're not sure why I'm using one unit of the graph, look up something called the unit circle, which is a circle of size 1 that fits essentially this bill. Now, if we've got the coordinates now sine of theta, cosine of theta, we can rewrite gradients as rise over run. Well, that's actually the sine of theta over the cosine of theta, and this is of course tan of theta. And so for this problem, rather than saying y equals mx, I'm going to say y equals x times the tan of theta, where theta is this little angle in here. Now the second thing we're going to need to know is that any matrix, and this is a matrix like a grid of numbers in here, simply tells you here what happens under transformation to the basis vector I hat, which is simply one unit in the x direction, like so. This is our I hat, and this here is what happens to our j hat, which is one unit in the y direction, like so. So this matrix I've drawn here says I hat becomes this vector, 1, 0, which is simply I hat, and j hat becomes this vector, 0, 1, under transformation, which is simply j hat. And so what I've actually drawn here is the identity matrix. If you multiply a vector by this, you simply get that original vector back. Now, what we essentially need to do is figure out if we have the vectors I hat and j hat and the line y equals mx, well, where does I hat go and where does j hat go? And then if we can figure that out, we can simply write in our two vectors next to each other in the form of a matrix, and that should be our final answer. Now let's give this a go. Okay, so what's going to happen here is we're going to have to figure out where does I hat go to when reflected in the line y equals mx for some arbitrary m. So here's y equals mx, and here is the unit vector I hat. Now I hat, let's say, is alpha angle away from this line. If reflected in the line is going to be reflected or rotated by another alpha and is going to end up sticking out here. Let's call this I hat prime. So I hat, which is the unit vector 1, 0, i.e. 1 in the x direction and 0 in the y direction, is going to become under transformation m, I prime, which is going to look a little bit like this. Well, this amount here is the y value of I primed, and this amount here is the x value of I primed. Now that's going to be, the x value is going to be sine of, x value is going to be cosine of 2 alpha, while the y value is going to be the sine of 2 alpha, a bit like this. And as a reminder, alpha is actually the angle of our line here, and so this is such that tan of alpha is equal to m, and therefore we can do alpha is equal to the arc tan of m. and this is going to be really useful later, but we'll see what happens when we get there. So that is what happens to I hat under the transformation M. Now let's do the same thing for J hat. So J hat is here. This is J hat, which is the unit vector 0, 1. Our line, again, is about here. Again, kind of arbitrary. Now, what is this angle in here? Well, this angle here is alpha, and so this angle in radians is pi over 2 minus alpha. Now, if reflected, J hat is going to end up about here. And this angle here is also pi over 2 minus alpha. And so now what is this angle? Now that angle there is going to be pi over 2, which is the full angle up to the y-axis from the positive x-axis, subtract pi over 2 minus alpha, and subtract another pi over 2 minus alpha. And that's going to be negative alpha, negative alpha. That's going to be 2 alpha. Then you've got pi over 2 minus pi over 2 minus another pi over 2 is just negative pi by 2. And so that is your green angle just in there. Now let's answer the question, where does then J hat actually end up? Well, J hat, which is the unit vector 0, 1, is under the transformation M, going to end up, let's call them J hat primes. Well, the x value of this vector is going to be the cosine of 2 alpha minus pi by 2, and the y value is going to be the sine of the same angle, so sine 2 alpha minus pi by 2. Okay, we now have all the information we need to write down the matrix which represents the reflection of the unit vectors in the line y equals mx. So as a reminder, here was the transformation of I hat, and down here is the transformation of J hat. And so let's put those together, and M is going to be, we simply write down a first column is the transformation of I hat, which is cos 2 alpha over sine 2 alpha. The second column is the transformation of J hat, which is cos 2 alpha, yes it is, yep it is, minus pi by 2 over sine 2 alpha minus pi by 2. Now, this is good. You can use this as the functional matrix and it's completely correct, although there's a small problem. We want to represent this in terms of m's rather than alphas or pi's or whatever else. And so let's figure out a way to do that. For that we're going to need some double angle formulae. So for that I'm going to say, and we should know this from standard A-level maths or whatever course you're in, so cos of A plus B is equal to cos A cos B minus sine A sine B, and similarly sine of A plus B is equal to sine A cos B plus sine B cos A. So let's firstly simplify this right hand side of our matrix, the column number 2. So just to save us some time, I've just written this out. So this is a sine of 2 alpha minus pi by 2 is equal to sine of 2 alpha times cosine minus pi by 2 plus sine minus pi by 2 times cosine of 2 alpha. Now cosine of minus pi by 2 is of course 0, and this is minus 1. This is sine minus pi by 2. And so the sine of 2 alpha minus pi by 2 is simply going to be 0 times the sine of 2 alpha, which cancels out into just being 0. It's going to be the negative cosine of 2 alpha. And so here is what we get for this one. And similarly for the other one, so cosine of 2 alpha minus pi by 2, that is going to be nothing other than the cosine of 2 alpha times the cosine of negative pi by 2, and we already know this is going to cancel out and become 0. Subtract sine of 2 alpha times the sine of negative pi by 2, which is negative 1. So this cancels, and this becomes positive sine of 2 alpha, like so. And so now, using these two identities, we can rewrite our equation slightly, or our matrix, sorry. So just down below, let me do that. So we had initially this thing, and we're going to rewrite that as follows. It's going to be this guy right here. So cosine 2 alpha minus pi by 2 becomes simply sine of 2 alpha, and then we've got sine 2 alpha, and then we've got negative cosine 2 alpha. Now if you know your reflection matrices, this looks a lot like a reflection. That's because it essentially is. It is a reflection in y equals mx, where alpha is based on the gradient, like so. Alpha is the arctan or inverse tangent of the gradient m. Now again, we're not quite there yet, because if I write in alpha equals arctan of m, well, I want to plug that into here and simplify. So if alpha is the arctan of m, then certain things are going to start happening. Let's first of all simply write this out. This is going to be so let's start with the sine of 2 arctan m. Using our double angle formulae from above, we can write sine of 2 arctan m is equal to 2 times sine arctan m, I'm going to start using some brackets just to make things a bit clearer, times by the cosine of arctan, and that's acquired by using our simple double angle formulae. Now let's draw ourselves a little triangle. Okay, this in here is the angle arctan of m. Now if I take tangent of arctan m, I simply get m, and that is equal to, from SOHCAHTOA, the opposite divided by the adjacent. Now let's just call the adjacent 1 for the sake of argument. That means that this is equal to m is equal to the opposite over 1, which is simply the opposite. Now I'm going to call this m. Now by Pythagoras, this is going to be the square root of 1 plus m squared. Therefore, sine of arctan m, let's use brackets more intelligently, like this, is going to be, from SOHCAHTOA again, that's the opposite over hypotenuse, which in this case is going to be m over root 1 plus m squared, and cosine of arctan m is going to be 1 over 1 plus m squared, like so. So this is our expression for sine of arctan m and cosine of arctan m. Now let's just put that into here, and we can say this is equal to 2 times m over root 1 plus m squared times 1 over root 1 plus m squared, which is 2m over 1 plus m squared. And similarly, cosine of 2 arctan m, well, using double angle formula again, that's going to be cos squared of arctan m minus sine squared of arctan m. Now this is going to be, as above, it's 1 over root 1 plus m squared, all squared, minus m over root 1 plus m squared, all squared, which is 1 minus m squared over 1 plus m squared, where m again is your gradient of your line in which you are reflecting these vectors. Now, using these, what I'm going to do is go back to our matrix and write it again. As a reminder, this is what our matrix looks like. So cosine 2, negative cosine 2 in the top left and bottom right respectively. Now that's going to become m is equal to this guy. This is from our cosine of 2 times the arctan of m. and then negative of that thing, well, I'm simply going to switch over the numerator, like so. And then in the top right and bottom left, we've got sine 2 arctan m in both cases. And that we decided was 2m over 1 plus m squared. 2m over 1 plus m squared and 2m over 1 plus m squared. And now this is simply 1 over 1 plus m squared, and the inside is going to be 1 minus m squared here, m squared minus 1 here, 2m, 2m. Now this works for any line with any gradient m, as long as it goes through the origin right in the middle. So we will do y equals mx plus c, where c is a non-zero constant at some point soon. But as a reminder, this was our problem, to find the matrix M to reflect vector v equals xy in the line y equals mx. Well, this is going to be, as we said, m equals 1 over 1 plus m squared, brackets 1 minus m squared, 1 plus m squared, sorry, m squared minus 1, 2m, 2m. That is the answer to our problem, which is quite a nice looking matrix, I think you'll agree. Thank you for watching, and I'll see you in the next one.